did that by thinking of 9:36 a.m. in terms of hours. Because if you're going to talk about the ebb and the flow of the tide and you really care about it, some cities in Kentucky, they're dealing with flooding right now. What you want to do is talk in terms of hours. That's how it happens. You know, it's not a minute-by-minute thing. You're not going to have somebody out there with a ruler in the water trying to see what's happened minute by minute. So then, if we change all of this into an hours situation, and we would happen to need this 3:48 p.m. Well, we can't use 3:48 because 3:48 or 3.8 would be over here. So what we'd have to do is we'd have to think military time. And military time gets to noon at 1200, and then 1 o'clock would be 1300, etc. So if we really did need to use that, we'd have to think, well, this is 12 plus 3, so we'd use a 15.8 for that time. But now we have the basics down. And we found A. We needed A. Can't write it without A. We found B, and yes, again, the clock was not my friend. The bell was not my friend. So we were starting to change this into a fraction that would be something that wouldn't have a decimal in it. Because in math, it is totally unacceptable to have fractions with decimals in them. They're two different systems. So we multiplied the top and the bottom of this by 10 to get 10 pi over 62. But then hopefully we noticed, hey, both of those are even. And that could reduce to 5 pi over 31. So now we have a nice A, we have a nice B, and we talked about H as being that phase shift of 9.6. And the vertical shift was actually the first thing that we found because we couldn't find A without it. So the vertical shift is up here, which means by just doing this little extra reduction, we're ready to write it. We've got it. So did they say we had to name it anything special up there? Well, let's just use d of x for depth of water. Let's use d. Or d of t, d of x. I think we'll stick with x since x is what we're going to use with our calculator. A comes first, 0.3. So I stop and think. Did we have to do a reflection with this one? No. Started high, so don't need a negative in there. And then we knew it was cosine because we wanted to start high. Then we need our b value, and our b value is this nice little 5 pi over 31. I'm going to need double parentheses here to get that to go properly into my calculator. And then our phase shift was 9.6 to the right, so that'll look like x minus 9.6. And then way in the back, our vertical shift of up 2.4. I think I could just squish that back there. Now, I'm not going to distribute the 5 pi over 31. This is obnoxious as it is. You know, there's a lot going on here. And it's ready for my calculator. So it's ready for me to start answering these questions. Now, you might not know that off the bat, but once you read it, at what time on the 4th of July did the first low tide occur? Okay, so that would mean I need to see where that low spot was. If I want to find where that low spot is, that would be a minimum. So I should be able to use my calculator for that. What was the approximate depth of the water at 6 a.m. and at 3 p.m. that day? My table will give me that. I can just use my table feature to find that information. What was the first time on July 4th when the water was 2.4 meters deep? Graphing calculator. You know, if we put y sub 2 equals 2.4, we'll be able to see the intersection. So, this big mess needs to go in here. I'm a little hesitant because the last 2 days I've used this. Third hour, it's crashed on my class both days. But hopefully, my computer has decided this will be fine this morning. Good, Smartboard. Everything's fine. We're going to be fine. No problems today. So there's our 0.3 and cosine. And that gets me thinking, wait a second. I wonder if I have this in radians mode. because I'm going to be punching in a pi in a second. And if I punch in a pi, I need to be in radians mode. Aha! This one's already in radians. If yours isn't, because we've done a lot with degrees recently, go down there, get your cursor on top of it, hit enter, back to y equals. Here's my 0.3 cosine. Now, I need my little fraction in parentheses. So, parentheses, 5 pi, second caret symbol, divided by 31, parentheses. That gives that little fraction that I had there. And then parentheses again for x minus 9.6. Parentheses, because I want the cosine of that whole mess. And then I need to put my vertical shift in there. 0.3 cosine 5 pi over 31 x minus 9.6, and I know I punched in a plus 2.4, but never hurts to take a second look. Got it. Window. Well, let's see. They gave us information about 9.6 hours. Then we had that other one hanging out there with 15. So when I was setting up my window a little bit earlier today, I just went with 20. 0 to 30 would be good too. We just want to see enough of the day. But the y's, remember the top of this curve was at 2.7. So 0 to 3 will be just fine for what we need. Beautiful little cosine. There it is. And you see, got the high up here. So now, we go back to the questions. At what time on the 4th of July did the first low tide occur? Well, there it is right there. And I have my pet cursor Blinky, and Blinky will tell me exactly where things go. Second trace, number 3. Don't be afraid, everybody. Blinky is hypoallergenic. Anybody with allergies, you're still going to be okay. Blinky is fine. All right, Blinky, we need to be on the left side of this valley. And hit enter. And the right side of this valley. And hit enter. And enter through guess. Looks pretty close. I mean, if we round to 3 decimal places, 3.400. But we have to take this and convert it back into time. So it's going to be 3 and 0.4 of 60, which would be 24. And then we need an AM or a PM. Well, that was part of that first curve, so that must have been an AM piece. So 3:24 AM. B says, what was the approximate depth of the water at 6 a.m. and at 3 p.m. that day? Like I said, that's the table. I mean, the reason to put it in there is to get all of that good information. So, second table, and they asked about 6 a.m., which would be right there. So we'll put 2.325, and this was given in meters. But for 3 p.m., we can't go to 3. That wouldn't make any sense. That was 3 a.m. So you have to think, okay, noon would be 12, 3 more hours, that's going to be 15. 2.124. Saves a lot of time, rather than having to plug in 6 for x and plugging in a 15 for x. So just use the table there. And then C says, what was the first time on July 4th when that water was at 2.4 meters? Well, I want to know, when did that hit 2.4? So I think about where 2.4 would be, because remember, we know the lowest spot was 2.1, the highest spot was 2.7. Got to be right through the middle there. And what I just drew tells me what I need to do. I need to go into y equals. I need to put 2.4 in there, and I need to see when they hit. The first time that they hit. Wow, looks like right after midnight. Right there. But let's let Blinky tell us exactly when that was happening. Second trace, number 5, intersection. Blinky's a little lost. I need to get Blinky closer to the intersection that I want it to calculate, or it won't know. It's a nice pet, but sometimes you have to be careful with it. And then you can just hit enter 3 times, because we've got first curve, and then it's definitely going to jump to the second curve, and a guess. Time was 0.3. Okay, that's not a time. So then we think, well, we need 0.3 of 60. 3 times 60, 180. Got a decimal point, 18. Well, we don't have a time that says 18 minutes, so it must have been right after midnight. And there it is. And you just reason yourself through everything that we have to do there. Now, as you get ready for the next section, I know my computer is going to have a fit if I keep all of this up there and try to open the next file that we have to do. So I'm going to have to close these things out and grab the next group. Alrighty, section 4.5. So, I don't think this is in your packet. I was flipping through the packet last night. Did this show up in there? Okay. So this is just a quick reminder that everything that we get for our graphs, sine, sinusoid, sine and cosine, or tangent, cotangent, cosecant, secant, this is where it comes from. I mean, this is exactly where we need to be. So as we move on now from talking about the sinusoids to graphing tangent, we're going to lose a couple things. And a couple of things we're going to lose, amplitude. Sinusoids have amplitude. They have a height of their curve. Tangent doesn't have that. We're going to lose phase shift. Phase shift is something that's only talked about with the sinusoids. So instead, we're back to talking about vertical stretches and compressions, and we're back to talking about those horizontal translations and vertical translations, but we're still going to refer to those as shifts. And that's because that's part of the language of the trig waves that we have. We refer to those as a shift instead of a translation. So now as I start thinking in terms of tangent, there's a couple of things I have to remember. Big one is that tangent of theta equals sine of theta divided by cosine of theta. Because on the unit circle, remember each one of these ordered pairs is cosine of theta, sine of theta. So I can get tangent by looking at what I have here. All right. Well, just like we did with sine and cosine, I'd want to use the nice ones. You know, anything that turns out really nice, I'd want to use. So if I have 0 as 0, 1, and coordinate trig also told us that tangent is y over x, any of those, we can use sine over cosine, we can use y over x, but we're going to have 0 over 1. So tangent is going to be 0 at 0 degrees. Well, another nice one that pops up halfway, square root of 2 over 2 divided by square root of 2 over 2, that's 1. That'd be nice to graph for tangent. But when I get to pi over 2, I'll have 1 divided by 0. Uh-oh, that's new. We have to put undefined. We keep going around, and we see, well, this will be negative 1. 0 over negative 1, that's going to give me a 0 for tangent. This will be negative, whoops, negative and negative, make a positive 1. This, negative 1 divided by 0, is undefined again. And then we have a positive and a negative square root of 2 over 2. for another -1. So we need to see how that comes together. And what on earth are these undefined pieces going to be? Those are vertical asymptotes. Tangent and cotangent have vertical asymptotes. And notice this is going to happen at positive pi over 2 and negative pi over 2. So it all comes back to this as we start talking about tangent, cotangent, secant, and cosecant. Obviously, way too much to do in one day. So we're going to take a look at tangent and cotangent today. We're going to find out they're a lot easier to graph than sine and cosine. So basically, we're going to hit this first one, but about that far, you know? And then it says, list the properties of tangent, cotangent, secant, and cosecant. We can't do any of that until we've actually seen all of these. It's going to be a while. Graphing transformations, we're going to start that today. We're going to start looking at transformations for tangent and cotangent. Use tangent, cotangent, secant, and cosecant models to solve problems. Yeah, we're a little bit away from that right now. We've just got to see the basics. So, right here, we see x and tangent x. And that's the reason on the last page here I went through with you what tangent would be. So when I see negative pi over 2, I remember, well, that was one of those goofy, that was undefined. But if I wanted specific values, like negative pi over 3, well, I'll have to look at that in a second. I like the nice ones, you know, when we had negative pi over 4. Negative pi over 4 was -1. Negative pi over 6, we'll take a look at after we get the nice ones on here. At 0, well, at 0, tangent was 0. At pi over 4, we had square root of 2 over 2, square root of 2 over 2. That was a nice one. And at pi over 2, we had another undefined. As for the rest of these, we'd have to put the two pieces together just like we did back when we took the first test, where we're thinking, okay, what quadrant are we talking about here? Are we talking positive or negative? And our special right triangles. 30, 60, and 90. It's very easy to see. The short side is 1, the hypotenuse 2. The other side is the square root of 3, and it's 45, 45, 90. These are easy to name, for it's 1, 1, square root of 2 in a triangle game. So let's see. Negative pi over 3. I just want to think pi over 3 for a second. 180 divided by 3 is 60. So I need the tangent of 60 degrees. Opposite over adjacent. But what quadrant was it in? Negative pi over 3. That's down here. Tangent is negative in the fourth quadrant. Pi over 6. 180 divided by 6, that's 30. So I need tangent of 30. Opposite over adjacent, 1 over the square root of 3. Well, we had to rewrite that enough. We know it's going to be the square root of 3 over 3. But it's in fourth quadrant. Needs a negative. Well, pi over 6, we just did that one. That's 30 degrees. The tangent of 30 degrees, square root of 3 over 3. Pi over 3, that's 60 degrees. We just did that one. It hasn't changed. You know, it's opposite over adjacent, square root of 3. And both of these were positive, so they're in the first quadrant, and they're going to stay positive. But as I look at this list, I again realize I don't want to graph square root of 3. I don't want to have to memorize that. I don't want to have to memorize the square root of 3 over 3. If I'm going to graph this, I want this one, this one, this one, this one, and this one. 1, 2, 3, 4, 5. When we were graphing sine and cosine, we found 5 critical points, and that was enough to graph them. Well, this is going to work. 5 critical points. Big difference. Tangent does not have a period of 2 pi. Tangent has a period of 1 pi. So if we need the period for tangent, we're going to have to use 1 pi over b. But these are the points that we just talked about graphed. And notice we have those vertical asymptotes at negative pi over 2 and pi over 2. Halfway between those two is 0. Great spot on our graph, 0, 0. And then we could use our nice negative pi over 4, negative 1 as a critical point. So we've got pi over 4 units separating this. The rest of them, I guess I just consider them fluff. You know, it's great that we know where they are, but the graph is going to show those points anyway at our negative pi over 3 and negative pi over 6. So from the table of values, we see the repetition that, hey, it started undefined and it ended undefined. That's where the vertical asymptotes are going to be. So when we're trying to find our starting and stopping points, we should use those to figure out where we need to go. And like it says, this means the period of y equals the tangent of x is only 1 pi. The graph is undefined for all odd n pi divided by 2. So it's not just negative pi over 2 and pi over 2. Now make it 2 pi over 2. No, not 2 pi because it said odd. So then you go to 3 pi over 2. Not 4 pi over 2, but 5 pi over 2. Which makes sense because it would be every 1 pi. We would add that. The principal branch of y equals the tangent of x is shown above. So let's just say that drawing weren't there. Here's what we would do. We'd say I need to write down pi over 4 and pi over 2. Negative pi over 4 and negative pi over 2. I need to remember that I'm going to have vertical asymptotes at negative pi over 2 and pi over 2, unless there is some kind of horizontal shift. And then I'll put on my nice ones. Negative pi over 4, negative 1. Positive pi over 4, positive 1. And smack dab in the middle, which is usually the one we start with, right there. Then we use the fact that we know what asymptotes are. Asymptotes are supposed to be lines that we approach but never cross. Ta-da! There's tangent. We don't need all the rest of them. Just the nice ones. Makes it go much faster. So now we need to look at the analyze piece. But before we do that, I want to let you know, tangent is easier to graph. When things are easier, our brain has to see it a few more times in order for it to say, this is important and I need to remember this. 2 things that students forget. That's a biggie. Everybody wants to keep using 2 pi over b, not for tangent and cotangent. The other are asymptotes are from negative pi over 2, then pi over 2. The graph is inside that, the negative pi over 2 to pi over 2. So when we look for our start and our stop, we want to think negative pi over 2, pi over 2 for tangent. So these are the 2 pieces that students struggle with remembering as we go through with tangent. Again, it all came from the unit circle. So if you ever forget, you could just go through the unit circle real fast and remember those. Tangent function. Let's analyze this puppy. So tangent is sine of theta over cosine of theta. Because it's a fraction and we can't divide by 0, it inherently has issues. So I think, well, when does it have issues? It has issues when the cosine of theta is 0. Cosine of theta, 0 here, 0 here, then it would be negative pi over 2. And we start to see, yeah, it's negative pi over 2 and pi over 2. That's where we get those vertical asymptotes. So the zeros of the cosine function. since it's sine of theta over cosine of theta. Give us those asymptotes. But we do get that nice 0, 0 point because sine is 0 right there. So you can have a 0 in the numerator. That's fine. It's just 0. But you can't have a 0 in the denominator because that's undefined. So this all comes from the definition of tangent as being sine of x over cosine of x. And now we get a chance to practice that again, where we said, okay, we've got pi, and we have to divide that by b. So in this case, if we're just talking about the parent function, b is a 1. And if we need 5 critical points, we're going to have to take a fourth of that. So we'd want our labels to be pi over 4s. Oops, better give myself some space here. Then we remember, asymptotes would be a negative pi over 2 and pi over 2. Ooh, if you have the other color, the extra color today, let's use that for asymptotes and for any vertical shifts that we have to go through today. If you have another color. And I think about that tangent graph, and I remember that if we went back negative pi over 4, we got to go down 1. I better stick with blue. And 0, 0, beautiful point put on there. And then if we went over to the right, pi over 4, we got to go up 1. And I know what asymptotes are. I'm supposed to approach them but never cross them. So I better look like I'm getting close to those asymptotes to make this work. So there's one branch of a tangent function. If we wanted another one, we would keep going over here. We had 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, which would be 3 pi over 2. The spacing needs to remain the same. So we had negative pi over 2, 1 pi over 2, and then they said use the odd ones, so 3 pi over 2 would be the next one. Right smack dab in the middle is where we get the 0. And then for tangent, I have to go back pi over 4 units and down 1. From pi, I have to go to the right, another pi over 4 to 5 pi over 4 and up 1. Now I have 2 branches. So this is our copy and paste. Copy this, keep pasting it, using those intervals of pi over 4 because this did not have any kind of horizontal stretch or compression. It's the parent. So now we need to talk about all of the wonderful analysis that we have here. And again, the big change for us, the period for tangent and cotangent is 1 pi, not 2 pi. We spent a lot of time on the sinusoids. So kind of got to get the brain to remember, wait a second, this one's a little different. Zeros. Well, let's see. This was at 0. This was at pi. It would make sense that the next one would be at 2 pi, 3 pi, etc. So, set of all x such that x equals n pi, where n is the set of all integers. And that makes perfect sense because the integers, remember, are -3, -2, -1, 0, 1, 2, 3, and on forever in both directions. And notice we're using number set notation when we do those. Vertical asymptotes. Okay, how are we going to do that? -1 pi over 2, +1 pi over 2, 3 pi over 2, Well, I kind of explained that. If we use the odd integers for n, but there's another way, and there are always multiple ways to write the number sets. X equals, you can think, okay, where would I want to start? And you usually use the first positive one to talk about that starting point, so that would be pi over 2. How do I get to the next one? Well, we know that. The period is 1 pi. So pi over 2 plus n pi, where n is the set of all integers. So don't forget that big Z there is all integers. We started the year with that, but it's been a long time since we did that. I'm gonna write that up here. We don't get any horizontal asymptotes. Domain, well, we'd have to leave everything but the vertical asymptotes in our domain. So we'd have to say it's the set of all x such that you can't use the vertical asymptotes. And the vertical asymptotes were pi over 2 plus n pi, where n is the set of all integers. So only change really between our vertical asymptotes and our domain is this little not equal to. We have to leave those vertical asymptotes out of the domain. Range, up and down forever. We're good. Continuity. Well, again, you'd say, but Cedarholm, I have to lift my pencil to draw this graph. You do, but the way around that so it can be used for calculus is to say it's continuous on its domain. So if you don't pick things that are vertical asymptotes, then you'll be able to do what you need to do. Continuous on its domain. Symmetry, definitely not even. Well, let's see. If I took this and rotated 180 degrees in a straight line across the earth, that matches. That's going to be odd. So it's an odd function. And remembering what we just did with the sinusoids, well, that means if it's attached to the x, we can move it out in front. It still has to stay there because it's odd, but we can move it. Doesn't have any local extrema. Tangent is increasing over its domain. Each one of these is increasing when you graph tangent. So increasing on each interval in its domain. Definitely not bounded. Up and down forever. So if you just put not bounded, you'd be okay. We were a little more specific here. Not bounded, above or below. End behavior. We can't do this. You know, end behavior is not going to happen. So for end behavior, we put does not exist. Unlike sine and cosine, where we could give somebody an idea of what was going on by telling them it oscillates between, we can't do that with this one. So hopefully by telling them, well, it's not bounded above or below, you know, you have to go increasing over the whole interval, maybe they'll figure out what it looks like if you're talking to somebody over the phone about how this works. So that's tangent. Now, before we even get any practice, we go to cotangent. Because cotangent just turns tangent upside down. Tangent is sine over cosine. Cotangent would then be cosine over sine. So let's see. Says the cotangent will have zeros at. 0 in the top is okay. That would be where the cosine is going to end up being 0. So now we're going to have zeros at pi over 2 and 3 pi over 2. We had asymptotes there before. So the zeros are the cosine function. Cotangent has asymptotes where sine is 0. 2 pi, 1 pi, 0. 0 pi, 2 pi. Oh, cool! Except it's different than tangent. So again, that throws first-year trig students because it's like, you're serious. With sine and cosine, we could always use, 0 to 2 pi, and things stayed the same when we were talking about our x's, not with tangent and cotangent. It's still going to be a period of pi over b. So tangent and cotangent do share that 1 pi for their period. But the asymptotes moved. They moved for cotangent because the denominator now is sine versus cosine. So asymptotes at the zeros of the sine function. Need to graph it. It's got a period of 1 pi. Critical points, I'd have to divide that by 4, so pi over 4. Pi over 2. 3 pi over 4. 1 pi. My asymptotes are now going to be at 0, pi, 2 pi, etc. So I'm using a different color for that. That kind of leans. That's not good. I know that I would only want to use nice stuff. And so what happens here is, where cotangent was increasing over its domain, cotangent will be decreasing over its domain. So here's our middle. If we go to the left one, we have to go up 1 with cotangent. And if we go to the right, pi over 4 units, we have to go down 1. So when I say 1, I'm talking about the increments that we see there. So there's cotangent. And again, you copy and paste that, and I wrote so big I'm not sure I'm going to have enough room here to... I won't have enough room to get another full... Maybe I can go this way. Usually we like to graph 2 of them, 2 curves. Oh, come on, Blue, wake up. And you just copy and paste. Now, sometimes in the problem it'll say graph 4 curves. It's just whatever the problem states. We like to see at least 2 when we're graphing. So, we're going to see a lot of repetition down here, but we also know we're going to see some new pieces to this. Still, period is 1 pi for cotangent, just like it was for tangent. Zeros. Pi over 2, 3 pi over 2. Hey, that's where the asymptotes were when we were talking about tangent. Yep, because we're flipping it upside down. So the set of all x such that x equals pi over 2 plus n pi, where n is the set of all integers. So now since we're turning tangent upside down, our vertical asymptotes will be where we had the zeros for tangent. So where the sine of x equals 0. Set of all x such that x equals n pi, where n is the set of all integers. So our asymptotes at 0, 1 pi, 2 pi, 3 pi, 4 pi, and into the negatives. No horizontal asymptotes. The domain, again, is just, hey, don't use where the vertical asymptotes are. So the set of all x such that x is not equal to n pi, where n is the set of all integers. But it is going up and down forever. Continuity on its domain, yes, continuous on its domain. Leave the vertical asymptotes out of it, and it's continuous on its domain. Symmetry. It's an odd function, so we can't get rid of the negative. We have to keep the negative. Local extrema? None. Increasing and decreasing. Cotangent is decreasing on each interval in its domain. Tangent was the one that was increasing. Boundedness. Nope. Not bounded above or below. And the end behavior does not exist. Does not exist. So lots of similarities, but some differences. All right, we got to graph one of these. Do we have time? You guys are out of here at 55. We have time. Tangent graphs fast. Okay, I don't want to graph fast because then I'm going to lose some of you. We'll have to call it. Which means I can't give you the assignment. I know that's a bummer. If some of you are like, I think I could do this, I'd wait. We haven't done this yet. I'll put it up there in case you want to write it down in advance, but we've got to get some experience graphing these. They are easier to graph than the sinusoids. Definitely are. But that was a lot of analysis to go over today for those two graphs. We have 3 days on this. We'll be fine.